Good time of day, everyone, and welcome to this new MLIR open meeting. And this week we have Gus Smith, who have been doing an internship at Google with Art, Tenpon, and Mangpo, who will present his work on an ML-driven auto-configurator for sparse tensor kernels in MLIR. Gus?
Great, thanks, Mehdi. Yeah, so like Mehdi said, I've been here this summer working with Art, Tenpon, and Mangpo on this auto-configurator. Word is kind of a mouthful, so if anybody has any better suggestion, please let us know. Also, this is my final presentation for my internship this summer, but this work is continuing on. So, any suggestions, any comments along the way, please let us know. None of this is completely set in stone. There's still a lot of tuning to be done and exploration to be done. So, like I said, please stop me at any point for questions, but let's get into it. Great, so let's start with a little bit of motivation. So I want to first look at, where does sparsity exist? So this project is all about automatically configuring sparse kernels. But let's take a look at where sparsity actually exists in the first place. So this is in a very narrow domain, obviously a very common domain nowadays, which is convolutional networks. But even just in a CNN, we're going to see that sparsity occurs in a lot of different places. So first, the input can be naturally sparse. It can also be kind of induced into sparsity. Depending on what type of network this is, we might be taking in graphs as input, which are naturally sparse. So our input to our network can be, sparse, can contain many zeros. As we go through our activations, we can introduce a lot of sparsity, whether naturally through operators like ReLU. Also, things like dropout create sparsity. Weights themselves can be sparse. They can be naturally sparse. We can also induce sparsity via pruning. And then also in training, the gradients can be sparse. So we see that sparsity, even just in this constrained realm of CNNs, sparsity is everywhere. And even beyond this realm, sparsity kind of pervades. And the interesting thing also is that sparsity takes a lot of different forms. So these are all just matrices, just 2D tensors, and we can see that there's distinct patterns of sparsity in each of these matrices, and this is just a very small selection. And so we can see sparsity takes many forms, and as we increase the rank of our tensors, you can imagine the forms of sparsity that we're going to see is only going to increase. But the good news here is that if we can exploit sparsity, it's immensely beneficial. So the red line here is really the one to pay attention to. This is a 256 by 256 matrix multiplication. And so if we just run it in its dense form, that's the blue line. We don't see any increase in performance as our sparsity increases. But if we actually take advantage of sparsity, that's the red line and the yellow line, we see at a certain point, around 80%, we cross over the performance of dense, and sparse dense. Taking advantage of sparsity actually becomes beneficial. And something like 80% sparsity is not uncommon in many different workloads, in deep learning especially. So this is certainly achievable and necessary if we want to keep increasing performance. So how do we actually exploit sparsity? What does it mean to exploit sparsity? Well, we use these things called sparsity formats. So sparsity formats are basically different ways of compressing a tensor, not representing explicitly the zeros of a tensor. One of the most common ways to do it is the coordinate format. So in this format, we essentially just pair the values of a tensor with their actual indices. So in this case, we know that the value 6 is at coordinate 0, 0 of this two-dimensional tensor, or this matrix. And there's a number of other different ways to further represent sparse tensors, depending on the actual sparsity present in the tensor. So different types of sparsity respond better or compress better with different sparsity formats. And there's a whole host of different sparsity formats. Some of them are just to handle general sparsity. Some of them are really specialized to specific types of sparsity, such as patterns of diagonals in the tensor. And so the list of specialized sparsity formats is long. And then to make things more complex, make things better, but even more complicated, along came something called Taco, which is the tensor algebra compiler. And so Taco really revolutionized in a lot of ways the world of sparse tensor compilation by introducing this dimension-wise specification of a sparsity format. And so instead of having these hardwired sparsity formats that you see here, they generalized sparsity formats so that you can basically specify them by giving a per dimension sparsity or compression attribute. So the way that a Taco format is specified is each dimension of our tensor can be indicated as sparse or dense, or compressed or dense. And then also we can define the traversal order over those dimensions. And so this combination of specifying compressed or dense for each dimension plus defining the traversal order over the tensor gives us k factorial for times 2 to the k formats for a single kth order tensor. So that really expands even further the world of possible sparse formats for a single tensor. So what does this actually look like? So this is from the Taco paper. So this is a single sparse matrix, so a 2D tensor. And these are all the possible formats represented in this Taco sparsity format. And so you get 8 different possible formats. Some of them are things we've seen before, so compressed sparse row, compressed sparse column. And then of course we just have the fully dense formats. But you can see, just from a single matrix, we have many possible formats. And as you increase the dimensionality of your tensors, as we're seeing happen today, and as our workloads are becoming more complex, you're going to just have more and more possible sparsity formats. So the world of possible formats to choose from for any given tensor that's being input to a kernel is really expanding. And the nice thing now, and this is where MLIR comes in, is thanks to Art and thanks to other people working on sparse compilation in MLIR, we can now really easily configure sparse kernels in an MLIR. So this is hang on, let me see if I can get my pointer working. There we go. So this is, imagine this is just your kernel definition in MLIR. So it looks fairly standard. It takes some input tensors, it gives an output tensor. There's some implementation in here, returns a tensor down here. Now all you need to do to turn this into a sparse kernel in MLIR to take advantage of sparsity is essentially you just tag one of the input tensors with a sparsity format here, which we can specify like this. And so you can see we have this kind of Taco style sparse format where we have a per dimension dense or compressed, and then also we have a dimension ordering specified here. And this is not all that you can configure in the sparsity format. So there's many other parameters that we'll talk about in a bit. But now it's thanks to this work done by Art, this configuration is incredibly easy. And so you can really experiment very easily with sparsity formats in MLIR. So now that it's so easy to experiment with sparsity in MLIR, the question is, can we configure its sparse format? Given a kernel, can we configure its sparse format automatically? And so what does that actually mean, to clarify here? So what does it mean to configure a kernel's sparse format? Well, what it specifically means is, so given this kernel, what we want to do is we want to assign sparse formats to the input tensors to that kernel. So for a given kernel, it's going to get a single sparsity format, for a given kernel, each input is going to get a single sparsity format, specifying whether each dimension is dense or compressed or et cetera, some mix of the two. And so the question here is, couldn't you just brute force this? Couldn't we just try every possible sparse format? Well, in some sense you could, but really what we would like to do is we would like to, first of all, we would like to quickly configure, we would like to do this quickly. We don't want to have to wait for trying every single sparse format on a host of representative tensors. Also, we'd like this to work over any kernel in some sense. We don't want to just take a kernel and then run an overnight process to check which sparse format is the best. We would like to, upon seeing a kernel for the first time, be able to quickly configure its sparse format. And really, here's one of the potential use cases is we could use it in a JIT if we had this auto-configurator that could do this quickly upon seeing a kernel for the first time. We could go ahead and use it in a JIT or some other instance where we need results fast. So the approach that we take to achieve this goal is we use a standard, what I see as a standard ML for ML approach. This is just kind of standard from my experience, maybe not in others, but the approach here is basically we train a cost model. So this cost model will essentially, given a kernel and the tensor inputs and the actual sparsity configuration, the sparsity parameterization, it will produce a prediction on the runtime or the performance of the kernel, some metric of the performance of the kernel. And then once we have this cost model trained, we'll actually use that cost model inside of a search procedure. And so the idea here is that cost models are fast to inference. They take a while to train, but they're fast to inference once you have them trained. And so this should really reduce the number of real experiments that we need to do, real measurements we need to take when trying to figure out which, when exploring the space of parameterizations. And so when I say, standard ML for ML approach, I'm basing it off of some papers I've seen recently. This does seem like a fairly standard way to do a search powered by ML. But again, here are some references for where I'm getting this idea from. So that's the intro. That's the goal here. The goal is to essentially build an auto-configurator driven by ML for sparse tensor kernels. Now I'm going to hop into the actual design details, but I think this is a good place to stop and ask if there's any questions up to this point. Good? Okay, great. So let's get into it. So I split this into two parts. The first part is training the actual cost model. Second part is using that cost model in a search. So let's get into the cost model itself. So we're going to first look at an overview of the entire cost model. How does it work? What are its inputs? What are its outputs? And then we're going to kind of go into detail about how we designed each component. So the cost model, the first question to ask is what are the inputs to the cost model? Well, we know at a high level, if we're going to be trying to configure a kernel, the sparsity formats of a tensor kernel, well, we probably need some representation of the sparsity configuration of that kernel. And in the world of sparse, the input tensors themselves also matter a lot to the runtime of a kernel. So we probably also need some kind of representation of the input tensors. So first, we look at the configuration features. So this is the configuration of the sparse the sparse configuration of the tensor or of the kernel itself. So the question here is, what features should we actually extract from the sparse configuration of the kernel? And then also, we're going to be another component of the inputs, like I said, is our features from the sparse tensors themselves. And so again, how should we extract features from the sparse tensors? Because the goal here is we need something that can be input into a cost model to actually generate an inference. So how do we turn a sparse tensor into a compact set of features that can be plugged into a cost model and inferenced over? Similarly with the configuration features. And then that's going to go into some neural network that will be trained to be our cost model. And the question there is, what network should we use? How do we structure it? How do we train it? And then that will produce a prediction. So this is, in general, is the shape of our cost model. So let's begin with the configuration features. And so this is actually fairly straightforward. So the sparse kernel configuration is pretty easily featurized. And when I say featurized, I mean turned into a format, converted to a format that can be put into a neural network to produce an inference. So The sparse kernel configuration is fairly easily featurized by just packing the configuration into a fixed length vector. So this includes things like the dimension level compression. So for each dimension, is it sparse or is it dense? The dimension level ordering, and then some other compilation flags and features and knobs, such as the vectorization level and the vector lanes, whether or not certain optimizations are enabled. These things all essentially can all be packed into a fixed length vector. And this is some examples of some of the features or some of the fields in the configuration. So featurizing the configuration is fairly straightforward. And so for sparse dense matmul, which is the kernel that we're focusing on today, there's around 9,000 unique configurations. So that's kind of our space of configurations to draw from. So sparse dense matmul is just a single two-dimensional sparse input to this kernel. So it's a relatively small space as compared to maybe a kernel that has more sparse inputs and higher dimensional sparse inputs. So next question is, how do we extract features from the sparse tensors themselves? So now we know how to extract features from the sparse configuration of the kernel. So given a way to configure a kernel, we can turn it into a fixed length tensor or a fixed length tuple or vector that we can push into a neural network. Now we have the same question for the actual inputs themselves, so this is where this work differs a bit from previous work. So, for example, in the Auto-TVM paper, they didn't necessarily have to turn the tensor inputs into features that can go into their cost model. And the reason here is that, in general, in a lot of dense kernels, the runtime or the performance of the kernel doesn't depend on the data inside the tensor itself. Whereas in the sparse world, the runtime of the kernel depends heavily on the actual distribution of non-zero elements within the sparse tensor. And so to have any hope of estimating the runtime of the kernel, we need to somehow generate features from the non-zero distribution in the sparse tensors themselves. And this is interesting because now we need, essentially, we need the user to provide a representative set of sparse tensor inputs to the kernel. And we'll talk in a bit about where we actually got those that representative set of sparse tensor inputs. So the question here now is, how do we extract features from sparse tensors? So given the sparse tensor that's going to be input to our kernel, how do we turn that into something that can go into the neural network as features? So we explored two different ways. We use two methods of generating features from tensors. So the first is the most straightforward. It's basically just a manual feature extractor. So given a sparse tensor, we have just a bit of code that extracts some high-level information from the sparse tensor. So things like the shape, the rank of the tensor, the number of non-zeros, really straightforward information that can be extracted. And so this produces a relatively small feature. It's just, essentially for each piece of data that we want to produce in that feature, we're manually engineering that extraction. And the other way that we approach to generating features from a sparse tensor is using a CNN. So actually, training a small CNN to automatically generate features given a sparse tensor. And so this is based on a number of papers actually have used a similar technique, used this exact technique. And interestingly, they use this technique to try to essentially classify, given a tensor, they try to classify, they do a classification problem, trying to decide which sparsity format from a set list of sparsity formats they should use to encode that tensor. And so our work is doing something very similar. We would like to use a CNN to generate features, but we're not doing a classification problem. We're actually going to use those CNN-generated features in a regression problem to generate a prediction on the runtime of the kernel given that sparse tensor input. And so it's interesting to see that this method has been used before in classification problems, but again, this is ours is a regression problem. So let's take a look at how this second method works. So how do we actually put a sparse tensor into a CNN? So we start with some variable-sized sparse input matrix. So we could be, the input to this kernel could be, if the kernel can handle it, it can be really whatever size. And so we need to figure out a way to turn this variable-sized sparse matrix into a dense matrix of a fixed size that we can actually do convolutions over. And so the constraint of needing it to be dense is purely just an engineering constraint. We are training with TensorFlow. TensorFlow does support sparse inputs, but it was much easier for our flow if we could actually input things in a dense manner. And so we wanted to somehow convert these sparse tensors into smaller, denser tensors. And so the method we used is from this paper IASPGEM, in which essentially they represent sparse tensor, and I'm sure has been used elsewhere as well. They represent this sparse tensor essentially with this density representation. And so what they do is they essentially block up the tensor and just do a pop count of how many non-zeros are in each region. And so now we can produce this fixed size dense matrix, and we can do convolutions over this fixed size dense matrix. And so yeah, so now we can perform dense 2D convolution, which makes our life a lot easier. Okay, great. So now we've seen how we form the features. So the input features to our cost model are just the packed list of configuration features. So the fields pertaining to how the kernel's actually configured and compiled, and then features extracted from the actual input sparse tensors themselves. So now the question is, how do we, what network do we actually use for our cost model, and how do we train it? So here's a picture of the network. Sorry, it's a little stretched and long here, but we're just going to go through kind of the components of the network. This is it's fairly straightforward. There's nothing too crazy going on here, but we're going to go over all the inputs and what's happening in the middle and the output. So first, we're going to look at the inputs here. So the input up here is the density representation of the tensor input that I was talking about. So this is a dense 2D matrix of a fixed size that we're going to perform convolution over. And so that's where this happens. So now we have a CNN right here that performs convolutions over this density representation to produce some fixed size feature vector down here at the bottom. So here's the feature vector generated from the inputs. And so this is a learned process here, where this network learns how to represent the input tensors using this CNN here. Now, similarly down here, here's the rest of the inputs to our model. So this is the feature vector generated from the parameterization of the kernel itself. So this is where all the density configuration information goes. This is also where we stick the manual features extracted from the input tensors themselves. So this is all just packed into a vector here. And so we concatenate the features generated from the tensor inputs with the feature vector generated from the parameterization here. And then we just do a simple multi-layer perceptron over those concatenated features. And then the output is some prediction. So here we have experimented with a few different things that we could be predicting and a few different loss functions, but here we're just predicting. Right now we're just predicting essentially the runtime of the kernel. And so now let's take a look at how this model is actually trained, the training flow of the model. So the space of data, the space of points that we could sample from is essentially the parameterizations cross the tensor inputs. And so we have, like I said, about 9K parameterizations for sparse dense matrix multiplication. And then we have 3K tensor inputs. And where are those coming from? Well, these are coming from a sparse ResNet50 data set from this paper listed here. So essentially, this is a representative set of sparse tensor inputs that you would see in real life used in a sparse dense matrix multiplication in real workloads. And so this gives us a space of about 27 million points to choose from. So far and away, plenty of room here for drawing a training data set and training a model. So what we did was we randomly sampled from the space, and we benchmarked the runtimes of each point we sampled. So we did this for about 50K points. So this is, for each of these points, we have a parameterization of the kernel, and we have an input to the kernel. So a sparse tensor input to the kernel. So we do this for about 50K points. 50K is just, that's the amount of time, that's the amount of points we could generate in the time we had. So in the future, we'll be extracting and sampling and measuring more points. And this was benchmarked on an Intel Xeon Skylake machine. And then we just run it through training. So right now, we're using mean squared error for the loss, but this is something we'd like to experiment also with in the future. So just a pretty standard training flow here. So that's the process of training the cost model. So I'll ask if there's any questions at this point, but otherwise we're going to move on to search. Any questions up till now? Okay, great. Thank you. Okay, so let's move on to search. So these figures are drawn from similar papers listed in the beginning that use cost models to do searches. And so generally, there's a similar structure here. There's generally some element of essentially exploring some space of configurations, selecting a space of configurations, running them through a cost model, doing some kind of experiment, and then using the feedback from that experiment to both improve the cost model and also choose the next set of potential candidates. So this is a kind of a typical format for these searches. So we use a fairly similar method here. It's a little bit simplified, but I will go through it now. So first, we randomly select test inputs, so test tensor inputs. So for the entire search process, we're going to just use a single set of tensor inputs to optimize for from our space of 3K tensor inputs. Then we also sample some initial parameterizations of the sparse kernel. And then for each search round, what we do is first we use the cost model to filter the set of candidates. So the initial set of candidates is very large. And so we don't want to do experiments on that entire set. We don't want to do real experiments on that entire set of candidates because those experiments are slow. And so what we do is we use the cost model to filter that set of candidates down significantly. And that process is very fast because doing an inference on the model is very fast. And then once we filter that down, we actually benchmark. We do real experiments on that filtered set of candidates. And so that's a comparatively slower process. And then from there, we record the top. And so this is also a filtering step. So we take the top measured candidates here. From there, we record the top benchmark candidates. So whichever proved to be the best after the measurements, we record those. And then importantly, we construct the next generation of parameterizations based on what we found in this search iteration. We construct the next generation of parameterizations to explore, and we repeat. So now just visually, so first we select this random set of test inputs that's going to be used throughout the entire process. We start with some initial set of parameterizations. They go into our model and they get filtered down. They go through the benchmarker and they get filtered down even more. And then finally, the sampler is what produces us a new set of parameterizations to explore up here. And just for a little bit more detail on how the sampling process actually works. So there are a number of ways to implement this sampler. This is kind of like the exploration module here. And so we've just tested out a few different ways. The way that we're using right now is that essentially this sampler, given two parameterizations of a kernel, it randomly forms a new parameterization from the fields of the two parameterizations. So in a way, it's kind of a genetic algorithm. So it's using the two hopefully good parameterizations, combining them, producing hopefully a better parameterization to explore. And so into the sampler, we essentially draw from the initial parameterizations from the start of iteration, the parameterizations that were filtered by the cost model, and then also the parameterizations filtered after benchmarking. So in a way, this is kind of like if you were presumably improving in quality as we move this direction. And then also, just to encourage some randomness, we also draw from all possible parameterizations. And the amount that we draw from each of these pools is configurable, and this is something that we're also tuning to figure out how much exploration should we do. We could also do kind of a simulated annealing in which we pull more from kind of the random pool earlier on in the process and pull more from the better pool later on in the process. But these are all configurable, and then that produces your next set of parameterizations. And so that's how the search procedure works at a high level. And so that's that at a high level is the design of this whole system. Like I said, there's still a lot of tuning and tweaking being done here. So results are still forthcoming. I really wanted to just talk about the design today and get feedback and input on the design. Some future work that we are looking at is first a huge component of this, and something that we were actually doing in the beginning, but I just had to I essentially had to focus on just one kernel for now, is we want to parameterize the cost model over many kernels. So the kernel itself should be an input to the cost model. And there are a number of ways to do this. Similar to how we extracted features from the tensors, we can manually extract features from kernels. We can also use, for example, graph neural networks to extract features from kernels. So this is a very obvious next step. And then also we would like to incorporate that into training data. So we'd like to train on data from multiple kernels, hopefully in the future even randomly generated sparse kernels and the features that come from those. That will really kind of diversify the data set that we have. And so with that, I'd like to thank you all for listening. I'd also like to thank Art and Penpon and Mangpo for all of their help and support throughout the summer. It's been a lot of fun. This has been a really interesting project, and I'm excited to continue working on it. So thanks, everybody, for listening. And I see that there are some questions. So let's see. Maxime?
Hey there. Can you hear me?
Yeah, I can hear you.
On one of the slides, you said that these search flows typically have a cost model improvement, like feedback loop stage.
Mm-hmm. Yeah.
You didn't mention whether you guys were doing that here.
Yes, sorry, we are not doing that. So that's also a great item of future work. So what happens usually is essentially after measurement, you will use those. So after measurement, you now have a new set of data. You've actually done real experiments. You now have parameterization and the actual runtime that it's produced. So why not use that new set of data to do another round of training on your module, essentially, or on your cost model is the idea. We're not doing that, but it's not too big of a step to. There's no reason we couldn't do that. It's just kind of a nice little added bonus to throw in.
Yeah. So the thing that I was wondering, so it makes sense that given new, like you're generating training data all the time. I was wondering if there was a direct. So I should just consult the literature, but I was wondering if there's a direct way to, I don't know, modify the cost, like improve the cost model by like fiddling with some parameters. You have a CNN, whatever, DNN cost model, so I guess you can't. you had some kind of more classical cost model, I guess you might be able to. Anyway, yeah. Thanks.
I could see. I mean, other people who have thoughts on this should also chime in, because I'm certainly far from the expert. Even with, some kind of neural network architecture, you could potentially, for example, add maybe a few layers at the end that you could, or somewhere in the middle that you could fine tune. So instead of trying to use kind of, this new batch of training data that you've measured to train the entire model for another iteration, you could essentially keep the model the same and then have kind of a situation-specific fine-tuning layer that you stick on at the end, and you just train those layers. That's something you could definitely do. That I think is maybe the neural network equivalent of what you'd be talking about with a more analytical cost model, that you could tune some parameters at runtime.
Yeah. Thanks.
Yeah. Thank you. Jeff.
Oh, I thought I lowered my hand. I was going to ask about using the kernels as input, but then you addressed that. Don't worry about it.
Yeah. No, that's a huge piece here, definitely. And we have basically all of the components needed to do that. I have a manual feature extractor that extracts features from kernels. It was truly just a matter of time. We didn't have enough time to draw data from SDDMM, which is the second kernel we were going to use, and generate enough training data from that. And in the future, we'd really also like to, I think it'd be really interesting to experiment with just randomly generated kernels, just completely randomly generated kernels. And there's no real reason we couldn't do that.
Do you have any, by any chance, do you have any data of how much performance improvement you're getting versus like manually pick configurations?
No, not right now, unfortunately. It's totally, so the search, there's a lot of knobs here, like I said, that are being tuned. And so depending on how I tune the knobs, I can the search either works very well or doesn't work at all, works in the reverse direction. And so I didn't really feel good enough about the consistency of the data I was generating to really say anything. One of the main components here is that the training the cost model itself has proven to be, because I mean, the cost model is kind of core to the search procedure, right? If you don't filter correctly, or if you don't filter in a sane way, if your cost model is just totally broken, your search procedure is not going to work. And so training the cost model has been a huge learning experience, definitely. Maybe unsurprisingly, it definitely was what ate up a good amount of the time this summer. And so I think that is kind of the root of our that's kind of where we need to focus a lot of our energy right now, is improving the cost model and making sure that the results that come out of that are sane. In the best of cases, they're accurate, and ideally in the worst of cases, where the measurement is not accurate, it's at least not totally implausible. So, for example, one of the issues I just ran into and just fixed was that the cost model was returning negative values for runtimes, which is a very basic and obvious error in a lot of ways, and it's going to lead your search procedure very astray by essentially making the search procedure think that these parameterizations are impossibly good. So there's still a lot of tuning work to be done here, essentially. Thanks for the question. Yeah, Maxine.
Sorry, how do you close the loop? How do you incorporate, how do you put this back into the MLIR representation?
Yeah, that's a great question. I mean, I think the real, where this could potentially be used is you'd have a very small, the hope is that you'd have a very small auto tuner or auto configurator that would be part of the sparse tensor compiler. I mean, that's not happening within the next few months, but that's the idea. Is you'd have this cost model that you train that would help you perform the search. And there's a lot of open questions here. So for example, our cost model is trained on very specific hardware. It's trained in a very specific environment. So do you need to train a new cost model for every environment? If you do, then you need to have kind of a repository of those cost models. The people at TVM who work on TVM have done a lot of work on this, both in training in different environments, but also showing some positive evidence to show that learning in different environments transfers to other environments, which is a good sign. Maybe that means you need to train on a smaller set of hardware environments. But still, yeah, there's the ideal case is that you'd have some kind of small and fast ML-driven search procedure that would help you automatically configure a sparse kernel, just seeing it for the first time, and that would be just a module in the sparse compiler of MLIR.
So the thing that I'm wondering, because I'm an MLIR noob, is that easy to do, where you can just plug in like this complicated, otherwise unrelated module into the lowering process?
Yeah, that's a really good question. I think in some ways there's no reason why this should be hard. There's some pieces here are very easy to get and kind of push off to a black box auto-configurator. So if somebody's configuring a kernel, then you're going to have the kernel. You're going to have you're going to be able to easily generate the space of potential parameterizations of that kernel. Some of the harder things, so that part is easy, getting that information, putting that into the search procedure, not hard. Some of the things that are harder here are getting a representative set of tensors, because that's a key point here, is a key thing you need in the search procedure is this representative set of tensors. And that's not necessarily something that we're going to encode in MLIR, right? So if you need to feed that into the search procedure, which you do, that will need to be done in some other way. So potentially this is maybe an optional, auto-configurator you could run after your compilation or something like that. But some components of some pieces of data needed to run the auto-configurator are easily accessible in MLIR, and there's no reason it can't be plugged in, but some aren't as easy to get.
Thanks.
Yeah, thank you. Lenny.
Hi. Yeah, thank you very much. This is a very interesting work. So I have two questions. So first question is, how do you construct the data set for the cost model? Like for your target model, like are you just using the Swiss sparse matrix collection, and then using those metrics from this data set, how do you construct the training data set?
Yes. So we don't use sweet sparse. That was something we considered using. We use instead this data set here. So I can send a link to the actual data set. It's on GitHub. But this paper, Sparse GPU Kernels for Deep Learning, from Trevor Gale, they have actually a large data set that's basically sparse tensors that are being pulled from the intermediate points of ResNet 50 and Transformer. So these are real, presumably real sparse tensors from deep learning. So that's our data set. Mm-hmm. And then, so that's our tensor data set. And so then, so we have about 3,000 tensors there. We have about 9,000 different parameterizations of a single kernel. So this is a sparse dense matrix multiplication. That's the kernel we're focusing on. And so this, the cross product of this is fairly large. This is like the space of all parameterizations run on all tensors. And so here, this is where we sample a parameterization, we sample a tensor, and we benchmark its actual runtime. And we do this for 50K points, just that's just the amount of time we had was to run 50K. We'd like to generate a lot more, and we can. There's a few different. There's a lot to be talked about here. About we're generating these 50K points in a very high fidelity way. So we're kind of doing less data but higher fidelity data. We're doing it on this machine, and we're essentially making sure the machine is very quiet. We're running we're only running this in a single process. We're not doing any process level parallelism, and we're gathering very high fidelity data. There's also maybe we could do this in a lower fidelity way and gather a lot more data. But anyway, so yeah, we have measurements for about 50K points, and then we just split that off into our training set and our validation set and our test set. So like maybe 40K, 45K training points or so. But yeah, so that's our entire data set.
Okay, so do they release their data set?
This data set here or ours?
Yes. This data set here.
I should have included a link, but I can put the link in the MLIR Open Design Meeting doc afterwards.
Okay, great. Thanks. And
but if you Google this paper title, you should find a GitHub link, and you'll find the data set there.
Okay, sure.
And it's a big data set too. That we are only using the ResNet 50 portion of it, but the transformer portion is even larger, which is really nice.
Okay, that's great. Okay, and my second question is that will you consider those kind of runtime configuration features in your cost model or different platforms? These kind of features, because if you only target a specific like hardware platform, you will have like how many cost models in your pocket, right?
Yeah. There's no reason. I don't see any reason that we couldn't. I'm wondering, like, what specific examples are you thinking of like runtime configurations?
Like for example, for MLIR runtime, it has various options, right? You can enable.
I see. Okay, so
right?
So of the runtime itself, yeah.
Right.
There's no reason that we couldn't put them in. There's even of the kind of features or knobs that we chose. There are still other things that we could have added into our parameterizations to make that space even larger. So there's no real reason we couldn't. There was just kind of a point at which we were like, okay, we have enough, and we have to stop. We have to stop somewhere. So I think the real question, and again, I'm very new to the space of building and training these cost models, but the real question is, what of those knobs are important for predicting the runtime? Which of them are going to be the most important predictors of the runtime or of the performance of the kernel? So doing some kind of survey, I'm sure there's some kind of survey we could do in which we basically consider all possible knobs that we could tune on, gather a bunch of data, figure out which things seem to be contributing the most, and then just use those as our set of features. That would probably be a more principled ways to go about this. But there's no reason we couldn't incorporate those runtime features. Even from a very practical engineering standpoint, it would be very easy to adapt our training pipeline to include those features as well. So yes, definitely no reason that we didn't. It's basically just a matter of we had enough and we couldn't consider everything.
Okay, sure. Thanks.
No, thank you. It's a great idea. Great. Any more questions? Okay, well, thanks everybody. Thanks for listening. And again, thanks to Art and Penpon and Mangpo for all their support and help this summer and continuing on into the future. It was a lot of fun. And thanks to all the broader MLIR community. This has been a lot of fun to work on this summer. So thanks, everybody.
So thank you, Gus. Great job. It was a pleasure having you, and I'm glad you're staying a little longer with us as well.
Thanks, Art.
Yeah, thanks for the talk today, Gus. That was great presentation, and great work overall. And thanks everyone for attending today, and see you next time.
Thanks, everybody.